complicated, but rewarding, really rewarding if you can do million times, million times. But like I tell you something, it was a more complicated not long ago because at the time we used also the tablet. Okay, I see that the connection is excellent connection. I think that I'm online. Stream settings. So it's looking very good. Stream is healthy, and so I think it. But no, I'm alive now in right lecture number 10. Okay, so I'm good to go. It is good now. All right, good. Yep. Okay. Hey, Mustafa, any chance that you can give me a little bit of coffee, like half a cup of coffee? Yeah, yeah. How did you like, by the way, the coffee that is in that lounge area? I agree. I agree. I agree. Yeah, I agree. Completely agree with that. Thank you. Appreciate that. Appreciate that. Okay, guys. Yes, I am. I am. Yeah. Now, let me just take myself to. How can I go to this? Is it like this is no my lectures? No, no, it's not. This PowerPoint. Yep. But you know, quite amazing that I can actually go back and forth even when I'm looking the OBS. Okay, this is the last one. So this is it. So it's gonna be the last lecture ever you guys gonna see from me. I don't know if it's gonna be last lecture ever, but it might be because there will be no more courses that I'm responsible of. You guys becomes to be senior member of the academic community. What happens next year is that you're gonna have some more additional courses in the fall, and then you're gonna focus on your thesis work. That's it. That's it. So last lecture. So now what I would do with this last lecture is that I'm gonna just 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 to put it a little bit up because it's cutting my head. Yeah. Okay. So I want to spend a few minutes about something that is called large deformation. We briefly discussed this in earlier occasions. Thank you, guys. I need to close roughly at 11:15 at latest because I have a visitor and I need to see this visitor. Yep, yep. So, but you can see the questions because the questions are not exactly they were a year ago. They're slightly different, slightly different. Yeah, yeah. So I'm gonna give this slideshow to you so you can do this voting action. Again, there's gonna be voting that you can vote the question that you hate the most, and the one you hate the most will not be in exam paper. And then the question that you like the most, and the one you like the most will definitely be in exam paper. So thanks, guys. Like I say, 11:15 latest. I need to be off. Sorry that been this semester been somehow busier than usually. A lot of traveling, a lot of visitors, so on and so forth. And I really apologizing that I've been using the substitute lectures and visitors. I think the visitors is a good idea. A substitute lectures, I guess it is. They can be refreshing too. Although that I really kind of insist to give a lecture by myself. I don't know why. I know that there's a different policies in different professors, but I'm the kind of the old school guy in that sense that I really wanted to deliver lectures by myself. All right. Anyways, so I'm gonna spend a little bit of time about this large deformation case to show you how is that this possible to describe something very challenging in a multi-body framework. And then the main body of today's lecture is, of course, how to prepare yourself to midterm exam. And I have all the questions that you were looking for. Those are rated in two different ways. Topics, well, each of the subject matters are rated based on the importance. And then the questions under that is also rated. Now, how you can prepare yourself the best way is that you look at the topics that are mostly getting the highest possible rate, and then you look at the questions that are under that particular subject matter that are highly rated. And so you do the math. So you're multiplying the stars together, and that's going to be your list of importance. So, all right. So that's what's going to happen in the end of the lecture, and yeah, that's about it. How was it? Did I? Because I really losing the sense of timing now. So did we discuss earlier about this, how to do the thesis work in a best possible way? We did discuss this. We discussed about career counseling and master thesis, how to do the master thesis work. Because I remember I explained about, I think, what was it there? Yeah, all right. All right, just before I getting started in today's lecture, this week, no, last week's Saturday, there was a homecoming day in the university. And I was in a homecoming day, and it was very pleasant meeting event. And we met a lot of former students, so a lot of alumni decided to visit us. And we had a discussion about what is that they're expecting us to teach. And of course, is you hear these stories that okay, the one thing that you definitely don't need is a strength of structures. This is something that is a waste of time and effort. I would like that's not going to happen. So we still need to keep this as a part of our curriculum. If no other reason, then the reason is that we need to give you lessons how to develop the self-discipline and to how to make yourself persistent and stuff like that. But then there was an interesting discussion about how they are hiring current students. And remember, I said that you shouldn't pay too much of effort and focus on one single course because they don't really look at one single course, but they look at the overall picture. And I said that the current students are worried too much about that they need to score high in all the courses. And I got an interesting information. So one of the guys from company said that when we hiring people, we like to see the whole variety of numbers in the final grading. They want to see 5, telling that okay, this guy is very interested in this particular subject matter, but they would like to see 1 as well. 1, because that tells that you actually have a sense of, like priorities in your life. So if you're scoring each of the courses, if you're scoring 5, it's not going to be very good for you. So it needs to be scale. Some of the topics they say that we couldn't care less. And we hope that the students have the same feeling. They couldn't care less. Diversity, correct. I don't know what are the courses that you should care as little as possible. I don't know. Maybe not necessarily elective ones, but it could be. Don't know what it is, but at least for Finnish students it's clear because we have 2 official languages in Finland. Because of this policy of 2 official languages, the one course that is mandatory is Swedish. And they say if you score high in the Swedish, they become to be suspicious. They did not actually mention this course in particular, but this is typically where you score very low. But maybe it could be something, I don't know. But I think it was interesting that they mentioned this diversity, this variation that would be good to you to see that you're scoring high and low. Because certain subject matters, you should put the minimum effort just to pass it. That's it. Okay. So, anyways, So you guys were here in Saturday, or you were not? You were not allowed. Really? Really? Okay. I see. I understand. Why not? Yeah, yeah, I understand. It was crowded already. It was very crowded already. And now, if you say that the current students too can come, maybe too much crowd. All right, lots of deformation. I'm going to be brief here. So I'm going to explain to you the method that is called the absolute Noda-Kone formulation. Remember that in computational dynamics, in multi-body system dynamics, everything started by making an assumption of rigid bodies. That was where everything started. And soon it became clear that, to make more accurate models, you need to describe flexibility. Typically, I mean, majority of the cases, the flexibility is not very large, so it's insignificant. Not insignificant, but it's small. And in case like that, where you wanted to describe the deformation, but it's not very large, you can use the floating frame reference formulation, the one we learned earlier. And you can use a model reduction together with the floating frame reference formulation. And then there are special cases, biomechanics, certain machine components, cables, drapes, so on and so forth, that you need to describe large deformation. And this is where the strain displacement relationship is inherently nonlinear. This is going to be challenging computational because this is approach, or this kind of the cases, you cannot use a model reduction. Well, let's say the model reduction usage will be complicated. So it's not going to be very straightforward because everything is nonlinear. So first of all, you have a large reference motion, which is a translation, not very complicated, but you have a rotation, which is inherently nonlinear in nature. And then you have a deformation that too is a nonlinear because of the nonlinear strain displacement relationship. And remember this, and the strain is like a displacement. How much is the deformation? And that's something that is not so easy to describe. There are methods to do that. And one of the methods that this university is focused a lot is called the absolute Noda-Kone formulation. I will shortly introduce this to you. I don't expect you to master this in a thorough manner for your information level. So how it goes. And yeah, so it's like this. So if you have a crankshaft, you can use a floating frame reference formulation. If you have a belt structure, this is a challenge in the model and sometimes needed. There you can use the absolute Noda-Kone formulation. Or alternatively, you can use a lump mass approaches, but this becomes to be computationally challenging because you need so much masses, and like we learned already that lump mass approach is computationally challenging because of the high frequencies associated to it. And these high frequencies will lead you to stiff models, numerically stiff models. All right, it works like this. So it's the simplest possible approach, and this is why it is pleasant to explain to you guys. Remember that in a finite element method, the way you describing the kinematics within the element frame is based on the shape functions and nodal displacement. Same here, except this is more general expression, because what you need to do in a finite element model is that you also need to have this transformation matrix that maps the element orientation with respect to reference frame. That is always needed. We didn't discuss that much, but that's needed to make the elements to have any orientation you want. But in the absolute Noda-Kone formulation, this orientation matrix, this transformation matrix is not needed. So it's automatically accounted simply by using the combination, linear combination of shape functions and nodal degrees of freedom. And it is, in that sense, it's easier, much easier to use than any of the conventional finite element method. Of course, it comes along with a certain complications, but it's simple like that. So you have a vector of nodal degrees of freedom. That's a nodal displacement. And then you have shape function matrix. A little bit different notations that we used earlier, because earlier we say N as a shape function matrix, and then U as a nodal degrees of freedom, but concept is still the same. How come it's possible to describe everything? I mean, the deformation, reference motion, translation, and rotation with simple linear combination of safe functions and not a degrees of freedom. That's possible because the method is based on the concept that is called vectorization. And this vectorization is really the core idea. How it goes? It goes like this. So in a conventional finite element model, where you have the safe functions and not a degrees of freedom, which is limited to your nodal, your element frame, is not capable to describe large rotations. Translations it can, but the rotation it cannot, without help of this transformation matrix. All right, so what we do? So this is based on the safe function components, and then the nodal degrees of freedom. So each of these components are scalars, scalar components. Safe function is a one single equation. The displacement in the y direction is a one scalar component. Partial y, partial x is a slope, is a scalar component as well. And then the another end, there is a displacement in the y direction, and then the slope that is describing like tangent of this particular point. So what we do then is that we're vectorizing. So instead of using scalar components, we are saying that, okay, these are now matrix representation. And this is a bit confusing, but it's a magic thing that happens. The scalar component, you have the exactly same component that you have in your conventional finite element safe functions, but then that is multiplied by identity matrix. That in a planar case, identity matrix is 2 by 2. Remember, identity matrix is something that you have one in diagonal component and rest are zeros. All right, so it's no longer a scalar, but it becomes to be vector representation. You do the same for other components. And then the really important thing is that instead of using scalar components in your nodal degrees of freedom, you're using vectors. So the point, this is your nodal location. You are not saying, okay, I'm interested in a motion in a y direction, but you're saying I'm interested in this point with respect to my reference frame. So it's including the translation, global x and y directions. And then you have these angles that are slopes. But then your differentiate is simply this vector with respect to x, which is a local coordinate of the element. That's it. That's what is needed. It's very, very simple. The difference is that, if you look at this is a vector, 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 vector. Each of the vectors consists of two components. So there is a total of 8 degrees of freedom in a one single element. So we started from 4, additional 4, and now is able to describe everything, including the reference motion. That's how it works. And that's the concept behind. Okay, so now I don't think we discussed this, but in a conventional finite element formulation, transverse Z deformation. You guys remember what is a transverse Z deformation? Kind of. Okay, so let me try to explain this to you shortly. This one. Now let me see if I can find my. This is where I am. How come I'm not able to see this PowerPoint anymore? There was this trick that you explained me last time. So it was like something alt shift. Yeah. Okay, here I am. Laser pointer bend. Okay. Consider this. So you're creating the beam structure by using thin layer of beams. That's what you can do. So you can easily build a thin layer of beams, and then you're binding them to. Let's say that you don't even bind them together. Let's make it this easier like that. So that just supported like this, and no binding here. And you're gonna introduce the force in the middle. What's gonna happen is that they're gonna slide with respect to each other. So that's what's gonna happen. And that's what the material is trying to do, and is not capable to do it because in the material they are not able to slide freely. So they are tight. Like you put the screws here, you know that the stiffness of this structure becomes to be much higher than without those screws. And now the screws are taking the transverse shear deformation into account. And this becomes to be important if you have a thick structure. Thin structures, it doesn't really make that much of a difference. Because you know that if, when you look at this deformation, when you have this kind of the layers, they have the significant difference here. So you need to kind of use a significant forces to make them in the same length. All right, that this becomes to be more and more significant if you're dealing with the thick structures. So this is what it calls transverse shear deformation. It's significant, and because it affects the deformation, amount of deformation in case of thick structures. So what they do in conventional finite element method is that they are not using this slope that is a function of the that is coming from the partial differentiation, but they're using separate angle, and the separate angle is interpolated within the length of the element by using separate shape functions. That's how it works. Now, transverse shear deformation can be accounted in this method that is called the Absorb-Noethern formulation by extending the concept of vectorization and not the dimension. And it means that, if you initially have these vectors that are partial r, partial x, you can introduce additional set of slopes that is partial r, partial y, which is a transverse direction slope. All right. Now this becomes to be interesting because now we have an element that consists of three vectors, each of the nodal locations, and each of the vectors consists of two components. So this end here consists of 6 degrees of freedom. This end here consists of another 6 degrees of freedom. So this is an element that is consisting of 12 degrees of freedom. It's a planar element, and the planar element, if I look at the one end here, the one single nodal location, it's quite interesting that I'm using 6 degrees of freedom for each of the nodal location. What they're representing, because you know that this nodal location can describe translation to direction easily and rotation very easily. Rest, because I just mentioned 3: translation, rotation. That's 3. What are the additional 3? Well, they are something that is not typically accounted in a conventional finite element method. Those are cross-section deformations that are now automatically accounted. So this method, when you're using this extended vectorization, if this is what you wanted to call it, it can describe cross-section deformation, or in the case of plates, it's a fiber deformation. Remember when I said that I spent, what did I mention, months in my life to try to create this shape function matrix. The shape function matrix that I was able to figure out at the time is based on this polynomial expansion. And you can imagine that this is a major headache to create the shape function matrix out of this. But eventually it was possible. It's this is, if you look at the Pascal's triangle, the selection of polynomials are not made in order, but there are one here, another here. So this is non-conforming elements, so which is making things even more complicated. All right, so that's how it's looking in a plate, but how they're looking in a case of beam, or what this cross-section deformation means. It means that in a three-dimensional space, we can use this distortion of the cross-section. Cross-section can shrink and it gets larger. So those are the things that can be do, and same for a fiber structure. So that's what they're representing. Of course, problem is that typically this cross-section deformation is associated to high frequencies. So this method is also getting easy. That is easily lead to models where there's a numerical stiffness. And numerical stiffness needs a special treatment to handle that. But that's how it works. All right. How you guys like about this? Okay. Then the story about Jussi Sopanen. Jussi was the guy that figured out that This. Let me explain it. So this paper here that it was my highest cited paper a long time was together with Ahmed Sabana. And if you make a list of most famous researchers in the field of multi-body system dynamics, first comes Ahmed Sabana, then comes nothing, then slowly the others. So he's like in a different league. So he's like really the superstar of the superstar in the computational dynamics. So he's really well known, very well known, and he's a professor in the UIC, University of Chicago, University of UI at Illinois, University of Illinois at Chicago. So how come I not remember this so clearly? Because I worked there too. Amazing stuff happens in your brains. All right. Anyways, so then Jussi came to spend a few months in UIC, and he got the simplest possible assignment to take a beam element and compare the beam element against the conventional finite element method, and just to verify that that is capable to produce a correct result. I mean, that the convergency rate is as good that we were expecting it to be. Jussi was not able to do it, and it was a big shame. Like, oh my god, this guy came from Finland, like I'm from Finland too, and he's not able to do the simplest possible task, and he just insisted I cannot do it. And then he left back home, and I came back home eventually after several years. And then he came to my office and said, I know why I was not able to do it, because the formulation is incorrect. There is a problem in the formulation, and because the problem is not able to converge correctly. And the name of the problem was locking. Very common problem in a finite element method. It's something that almost each of the finite element elements are suffering from lockings, particularly the ones that are describing this transverse shear deformation. It's very, very common. And typically the way you do this, or way you're solving the problem is that, what you do in a finite element method is that when you're computing the components in your elements, stiffness matrix, mass matrix, let's say stiffness matrix is the most relevant one. You do that by using numerical integration scheme. Gaussian integration scheme. And what you can do in this scheme is that, first of all, it's based on the points. You're selecting the points based on the number of the highest polynomial component in your equation. And then it's accurately capable to do the integration. But what you do when you have this locking is that you have the problem in your kinematics, and you're fixing that by integrating your element incorrectly. So you have a problem, and you're fixing that, making a mistake. Or mistake that is you're compensating making another mistake, intentional mistake. And that's how you can get rid of the locking. And this was the way that this can be solved too. And this was the paper that we put together with Jussi. And it's no longer the most cited paper, but was really a lot cited paper because of the problem. So it was explaining that it is incorrect, that the method is not capable to do things correctly. All right, so that was the story behind. So Jussi, think about how big is a pressure that you come and work together with the biggest name of your field. You're not able to do what the biggest name is asking you to do, but you need to find try to see that everything is correct. There is a big temptation to just cut the corners and say, yeah, it seems to work fine, but not Jussi. Remember what we learned about this bicycle dynamics and this Sommerfeld book series about gyroscopic forces, that he too made a mistake. The people do mistakes. There is a human nature. So it's important to be suspicious, to think whether or not this is a real case. All right. So then the applications are like belt structures. These are the typical cases. Animations are not running here today because of what I'm clicking. What? I think it is because of the pen. I think it is this one. I need to take this pen off. Yep, this was a reason. So they're like belt structures with the plate elements. This is from the Xerox machine. These are the applications. the Xerox machine is not willing to run, but others are running. So that's what you can do with this. You can also use it in a cable structures, and you can use something that is a big promise. And this big promise is this ALA this abbreviation comes from arbitrary Lagrangian Eulerian formulation. And this is a formulation that you can change the element length. I mean, you can always change the element length when you do the initial modeling, but during the course of the simulation, you cannot do this anymore without introducing strains. But this arbitrary Lagrangian Eulerian is a method that you can change the element length while simulating. Now, this is a big advantage because what you can do then is that when you're modeling the free length of the beam like cable here, you can simply change the length of the element because there you don't need that many elements. Whereas where you're in a close connection to bullish system, you need more elements. And this is the method that can take this into account. Very nice method. So it's really something that makes sense to use. And yeah, but not going to explain any further information about that. Then another applications are catenary systems that are in the belts, tires, of course, because in tires you have a large deformation. And something that is quite surprising too is a leaf spring. Leaf spring is still used in the heavy trucks, not sure about heavy machinery, but in trucks and in American cars, not in the European cars. Yeah, they still do that. It's a technology that is not so advanced, but seems to work fine. And I think it is very affordable technology. And and that's something that if it's like this transverse Z deformation, because this in a leaf spring, these leaves are intentionally sliding with respect to each other. There's a spring with a certain amount of damping. Of course, you need the separate damper in addition to that. But it's really, really hard to model by using any other method than this one. And then comes biomechanical application, electronic, when you look at this kind of sensor technology, when you have a fluid applications, optimization, and manipulators, you can use it. And then the latest is that it have a close relation to something that is called isotrigonometric analysis. Okay, here's the deal with isotrigonometric analysis. Remember, in a finite element method is all about polynomial expansion. We're always getting started from polynomials. And we have the problem because, most of the geometry description is based on CAD software. In the CAD software, they're using NURBS, which is non-uniform rational B-splines. That's where that is coming from. So with NURBS, you can describe more complicated geometries than comparing the polynomials. But this is a mismatching because you have the geometry described in CAD, like this man. You take the geometry to finite element software, you do the meshing, and then you're realizing that no, it's not very good because the meshing is making too many elements to this kind of detail. Or let's say that there's a hole somewhere in your structure, so it's the meshing tool is getting confused. You need to go back to your CAD software, take the hole or some of the details off to make sure that your meshing tool is cooperating better, and you go back and forth a number of times. So it's not very productive. And actually, the meshing, when you look at the finite element modeling, seems to take most of the time. So meshing is complicated. So now there is an idea. So what if we forget about polynomials and start using NURBS initially in finite element? Yeah, that's possible. So you're using non-uniform rational B-spline as a fundamental of your element, replacing the polynomial expansion. And then you have the same language, let's say the same background in your CAD description and your finite element, and your meshing becomes to be more convenient. This is still something that I haven't seen much in as a commercial software, but I believe that it comes with a big promise because the meshing is supposed to be more smooth once you use that. But it's all based on the NURBS. So that's what this is based on. And now you are able to describe more complicated structures in finite element modeling, and your meshing will be smooth and so on and so forth. So that's what this is about. All right, summary is this. So the method is based on this vectorization, and you can do the vectorization in a 1 or 2 dimension. 2 dimension if you want to capture transverse Z deformation. Okay, applications are vehicle dynamics, biomechanics, rotating structures, optimization, multi-physics, cables. This is my question. In isogeometric analysis, finite elements are based on NURBS, polynomials, trigonometric functions, or imaginary functions. Oh, hold on. So it's not yet on. So again, window tab. So window tab. Alt tab. Hold on. So here's my live streaming. So let me put my. It's LUT2. So just a second. Squeeze. Hold on. So you're not able to get in yet, but momentarily you are able to do so. You know what will be the best summer present to me? You don't know that. The best present to me would be you guys scoring 100% in the last in-class quiz. That would be really fantastic. Really? But what are the choices here? Think about the choices here. So this is different than conventional finite element method. So if this is different, it cannot be something we learned earlier. So that leaves you two choices. No, three choices. And which out of the three choices is correct? Yeah, imaginary functions we have not mentioned a single time. Yeah, because they're imaginary. Correct. Trigonometric function we did mention. Okay. Okay, they cannot log in. So okay, so it's LUT2. So the room number is LUT2. LUT2. Okay, why don't they use this instead of finite element? They do use this isogeometric analysis instead of, it's still finite element basis. It comes with a problem too, because the beauty of the finite element method is that this not a degrees of freedom has a very clear, simple physical interpretation. And this is simply because of the polynomials. And as you move away from the polynomials, the interpretation becomes to be less clear. It's not so clear to see what is that you're solving. Remember, if you're solving the polynomial, this A0, A1, and A2, if you get that, you don't really know what is that. How is a deformation end of the day. Of course, you can use a post-processing techniques to make a better interpretation, but it becomes to be complicated. You mean this isogeometric? You're asking that? It's a formula. Okay, that's what they use. I was not aware of this. It could be, but you said that that's in CFD. In MATLAB. Ah, okay. Yeah, sorry, I don't know. That I don't know. Okay. Okay, so let me take myself away from this. Alt tab. I'm here. So I'm gonna take this away and let me show you the last set of slides. Good midterm exam. Here are the subject matters, and you see that some of them are rated as a 5-star, some of them as a 4-star, and then 2-star. So I have a list of questions for each of the subject matters. So what you really need to do is take a look at this. Take a look at this and to see if you are able to answer that. And if you are, that's very good. So what are the typical applications of biomechanics? Give examples and explain what purpose the biomechanical studies serves in present day applications. Now, I think that you can do that based on what Adam explained to you. Compare the biomechanical simulation possibilities with experimental studies. That's a good thing because some of the experimental things it's going to be very violent because the subject is human, and you may not get the permission from ethical committee to do some of the studies for human because you're not able to make people to suffer too much. All right, and then what are the building blocks of biomechanical models? How do they compare to simulation models of machines? They're almost the same. Steel structures, bones, actuators, muscles, control system. That's very complicated. That's no comparison really. All right, and then take a look at these are the slides from some of the things about Adam. Really, in the biomechanics, what you do need is that you need to get you need to get the motion data one way or another because the building blocks that is complicated in the biomechanics is control scheme. This is really, really complicated. And we really cannot model the human motion by making a representation of brains. That's way too complicated, at least in the current knowledge. Maybe later when the AI technology becomes to be even more advanced than it is at the moment, you can do it, but not now. And the way we do this is that we have a motion data. We can get the motion data by using camera technology or IMU measurement. Those are typically the two choices. Once you get the motion data, then you're forcing your model to replicate the motion. And that's just the way you're teaching your muscles to do the motion. And then finally, once the teaching is done, you can release the teaching mode and let the model to go. And then you can dive into the different details of your model and you see how well it works. And you can predict the things that are otherwise difficult to get. All right, bicycle dynamics. The first thing is that, what happens when you do the steering thing, where the energy goes, the steering. Remember, we learned from Arden that if you do the heavy steering, this is the way you can make your bicycle to move forward. So it's going to forward motion. That's answer the first question. And you remember if you wanted to turn right, you need to, how you can do this? If you want to turn right, first you need to turn left. That's how it goes. Okay, so simple things. Okay, modal reduction. How does the modal reduction reduce the computational effort? So what's the mechanism behind? You need to understand, okay, you're reducing the size of your model and you're making it more pleasant, numerically more pleasant, two ways. So you are reducing the interactions between the degrees of freedom, and this is the way you can play with the frequencies. So reducing size, you're making numerically more pleasant, and those are the mechanisms behind. Of course, you're making a compensation in your accuracy, but that's one thing. Okay, what are the key steps in Craig-Punter method? It's like this. So you're first selecting boundary degrees of freedom and interior degrees of freedom. And based on this selection, you reorganize your stiffness and mass. And based on the reorganization, you're comparing the unit displacement for boundary degrees of freedom, and then the eigenvalue analysis for interior degrees of freedom. And you're combining these two packages, and that's your modes. And if you're not happy with the fact that your unit displacement modes, or the modes that are coming from the unit displacement, are not orthogonal, you can force them to be orthogonal with help of the monster technique called orthonormalization. So first you get these two set of modes, fixed interface normal modes, static correction modes. These are not orthogonal, these static correction modes, but you can force them to be orthogonal. Not a big problem in my mind. But anyway, so you can use orthonormalization to do that trick. Not a big problem in my mind, because really what matters the most is that you're reducing the size of your problem. And you still have this ability to affect to select the modes in such the way that your frequency content becomes to be pleasant. It doesn't really matter in my mind so much that they are not orthogonal. But again, if you really want to make everything as beautiful as possible, then the orthonormalization comes into play. All right. Contact modeling. consists of two components. First, you have to make predictions about whether or not the contact takes place, and if that's the case, then you have two choices to describe the contact event itself. Choices are penalty forces or cone complementary approach, which is based on these inequalities. So explain the concept of bounding boxes. That you have bigger boxes, smaller boxes inside of the bigger boxes, and so on and so forth. That's how it goes. And penalty forces are simple the forces that are based on the penetration. Penetration actually doesn't happen in a real life. I cannot push this inside of these two components. I cannot push this pen inside of this remote. It's not going to happen. And if I really use a lot of forces, which I could because of, not saying what, I'm saying the big muscles. Okay, anyways, if I really use a lot of forces, then they will deform. But again, the penetration is not real life. So this penetration, that is an imaginary thing. So we making these two bodies to be rigid, and then we assuming that there is a penetration. That is like indentation, that we're thinking that is a describing this deformation that comes into play if really high forces are used. Now the penalty forces are kicking these two bodies away from each other based on the penetration. Simple like that. What are the advantages, disadvantages? So advantages is that it's simple to model. Disadvantage is that high mass differences. Let's say that you have a military tank that weighs 50 tons. You have a piece of sand that weighs 1 gram. They don't work well together because, again, it's about the forces. And it's hard to make it in a way that the small mass variation work the way you want. Okay, many body dynamics is a method that using, like the title implies, millions of particles. And then using these inequalities to describe the contacts between the particles, that's the way to go. Contact description, this is what we discussed earlier. Penalty forces, on complementary approach. Stress analysis in multi-body dynamics, how the stress histories can be evaluated by using multi-body system dynamics. So these are the ways, two ways you can do. You can extract the forces from the dynamic equilibrium phase. You can take these forces to your finite element model, and you can compute your deformation. You actually redo what you actually did already in your multi-body formulation, or alternatively, you can use something that is called modal stress matrix, where you take the P vector, which is a modal decrease of freedom. You compute the nodal decrease of freedom. From nodal decrease of freedom, you have the kinematic matrix, the B here, that tells you how are the strains. Elastic coefficient is in this matrix, and that gives you the stresses. Way more straightforward, way more easier to use. Okay, multi-body dynamics in fatigue. Why welded structures are vulnerable for fatigue damage? Two reasons. Because welding process itself is not a perfect process, but because this process itself is introducing the initial cracks in a welded joint. Because there will be, combine the product particles and others that are not perfectly combined with the two bodies, and this acting as an initial crack. Also, because the violent process of welding, you're introducing a lot of heat to your welded joint, and because of the heat itself, when the heat is going away, there's going to be very high residual stresses. And high residual stresses are typically in a corner when there's a stress strain curve moving from linear to nonlinear, very locally. Again, very, very locally. And that's why it doesn't really help you much if you use a high strength steel, because the residual stresses will be, again, in a corner where the linear range tend to be nonlinear. So that's the reason behind. Two mechanisms, two reasons for that. And how you can do the rain fatigue analysis is that you need to get the stress history that we learned in the last slide how to do it, and then you're doing the rain flow analysis to see what are the range of how much the stress is fluctuating, what are the delta stigma. This is really important to understand, because without the delta, is not very harmful in terms of fatigue. But if the delta is large, then there's a high risk for fatigue. And then you just compute the fatigue based on the pre-calculated tables, and that's how it goes. And then large deformation analysis. What is it? Why, when transverse shear plays an important role? When your structure is thick. That's an answer. What's the concept of isotrometric analysis using the NURBS instead of polynomials? Explains shortly the kinematics using the absolute coordinate formulation. That's the function matrix multiplied by nodal degrees of freedom. All right. That's it. Then, oh, hold on. Then you're present to me in my summertime. Looks like this. I want to thank you already in advance. I really appreciate that you scored 100%. So this is a fantastic treatment to me. And now I know that you love me because of the 100%. Right? Where is my, how can I see, where is this? So the results. There. Okay. Very good. There's a lot of love in here, a lot of love. Not 100%, but that's okay because, this is very good. Great. Hey, then I need to, so what should we agree about the exam? Yeah, but when we're gonna have the exam? A week again? Sure. Um, yeah, but let me check out the calendar. So when would you like to have it already next week, or you know in, so you're saying that next week will be good one week exam. So 1 week and you have one attempt. And I'm saying that we can get started in a week. That is the Monday is 22nd of April, so that's going to be next week Monday. Open it then and close it on 29th. That's one possibility. Alternatively, we can get started in a week after that, Monday 29th. But that's when you have then that's when you're gonna have these Labor Day party. I mean, these Vappu parties. So you guys are wasted. So you're not gonna score that high in exam if you do it while partying. Is it okay? Next week. Okay. So what happens is that you're gonna get this questionnaire. What's gonna be the exam? I mean, the question that will be for sure there, and the question that will not be there. Oh, okay. We'll do it. So they're not there. All right. Okay. Tomorrow I'm gonna head to Helsinki to give my fingerprints in Chinese embassy. So I think that I could do it while I'm traveling to Helsinki. And can somebody complain if it is not ready on, let's say, Friday afternoon at latest? Okay, yeah, but it's gonna be my to-do list. All right, guys. Thank you very much for the big love. Appreciate this high percentage. Good. And we're gonna see in corridors, not in the lecture rooms. We'll see. We'll see. Okay, guys. Thank you very much. See you around. Okay, so end stream. I'm gonna close it from my OBS.